Good day, everyone. I want to welcome you to another section. In this video, I'll be talking about another aspect that we also need to take with in spectroscopy. Basically, Beer-Lambert law is a principle that guides spectroscopy, especially when it comes to spectrophotometer, and it relates absorbance to concentration of substance and also to path length. To start with, Beer-Lambert law states that absorbance is directly proportional to concentration of substance in solution at the same time to path length, which implies that A, which is our absorbance, is proportional to concentration either in mole per dm cube or gram per dm cube and path length. Now, with this relation, we can therefore say if we introduce a proportionality constant, then we can see that A equals to epsilon CL, where epsilon is the proportionality constant. But in this case, we refer to epsilon as either absorptivity or molar absorptivity, depending on the unit of the concentration. If the unit of concentration used is gram per dm cube, then your epsilon will be absorptivity. But if the unit of concentration used is mole per dm cube, then your epsilon will be molar absorptivity. Now, you can always use this expression in determining concentration of substance when we subject it to spectrophotometer. That is important. As much as we know the path length, we know the path length, we know the absorbance, or at the same time we know either the absorptivity or molar absorptivity. In the other way around, but the expression can be used to determine any of the mentioned quantities. Sometimes it can be that we have to calculate the absorbance when we are given concentration, path length, and at the same time absorptivity or molar absorptivity. But most commonly, epsilon is usually taken as molar absorptivity. But don't forget what I've said, that it can either be absorptivity or it can also be molar absorptivity, depending on the unit of concentration. If the unit of concentration you are using is in mole per dm cube or molarity, then it implies that your epsilon will be molar absorptivity. But if the unit of concentration used is gram per dm cube, that means that your epsilon will be ordinary absorptivity. Another thing also to take note also is the fact that absorbance measured in spectrophotometer can also be related to intensity of light, because in spectrophotometer, let's assume that we have a sample inside our cuvette, and then you have the incident light with with intensity I naught. At the same time, that passes through the sample that is present inside the cuvette. By the time the light travels through this particular cuvette, then the intensity of that light will have reduced. Let's call the light that emitted the transmitted light, and that some of the light that incidents on the substance or the solution in the cuvette will be absorbed, and that reduces the intensity of light. So the transmitted light will have another intensity, let's call that I, or let's call it IT, either of the two, just to indicate that it is the transmitted light. But like I said, because the incident light passes through a particular this solution, some of the particles within the solution will have absorbed some of the light that is incident on it, and that means that the intensity of the transmitted light is very low compared to the incident light. But the major thing I want to bring out there is that absorbance can also be related to these two. It can be related to the intensity of transmitted light and the intensity of the incident light. From this place, we can say that if we know the intensity of the transmitted light and the intensity of the incident light, therefore we can say that transmittance, which is also a very important quantity, equals to high T over high naught. Now, transmittance is help us to know how much of the light that incident on solution is transmitted, but most times it's usually given in percentage. So by the time you find the ratio of transmitted light to the incident light, to the intensity of the incident light, you can report your answer in percentage. But because if I know the transmittance, or let me say if I can measure how much light is transmitted, I can also know how much light is absorbed by taking the reciprocal of the transmittance. Therefore, we can say, and that's why we can say that absorbance A can be equals to logarithm of 1 over transmittance in base 10. So in a way, we are trying to say that the reciprocal of transmittance is absorbance. But the only thing that we only added to it is that we are taking the measure in what? In logarithm. That's the only thing that we added. So we can simply say that absorbance also equals to log 1 over transmittance to base 10, which implies that our A therefore can be equals to log base 10, and then we are going to have I naught, the intensity of the incident light, over the intensity of the transmitted light. So, and that's where I'm going, in the sense that absorbance, apart from being related to concentration and path length, can also be related to intensity of light that is incident on the sample, or let me say on the compound that we're trying to measure, and the light that was transmitted after absorption has taken place. So this relationship, this first expression and this expression are very important thing to note when we are trying to work out, probably try to measure the concentration of substance using spectrophotometer. After talking about things that we have under Beer-Lambert law, which are said in the summary, relates absorbance to concentration of substance in your solution at the same time to path length. And I've also tried to show us the relationship between the absorbance and the intensity of light that incident on a particular sample, and the intensity of light that is transmitted after absorption has taken place. So at the same time, we must note that absorbance, it does not have any unit. It's just a quantity that helps to measure the amount of absorption that takes place during the use of spectrophotometer. But the essence of it is that it can be used to determine the concentration of substance that is present in our solution. Now, we are going to be looking at an example based on what I've explained so far, how we can apply the formulas I've given to us from Beer-Lambert law. First, in the question, we are given that a solution of 4-methyl-3-pentanetone in ethanol show absorbance of 0.52 at 236 nanometer, which is the wavelength, in a cell with 1 centimeter path length. Its molar absorptivity at 236 was 12,600. Find the concentration in gram per dm. The first thing to do is to try to identify the compound given, which is 4-methyl-3-pentanetone. So what is the structure of that compound? The parent name is pent. It starts with pent, so that means you have 5 carbon system, which is C. Now, the parent name also indicates that there is a ketone functional group on carbon 2. So let's say this is carbon 1, carbon 2, so you have double bond O there. At the same time, the parent also shows that there is a double bond in the system which is located at carbon 3, but that implies that the double bond is between carbon 3 and carbon 4, so we have a double bond here too. At the same time, we have a substituent which is 4-methyl, so there is a methyl group on carbon 4. So this is carbon 1, 2, 3, 4. So we have CH3 here. So it just complete the system. So we have CH3, we have H, we have this, and we have what? We have H3. So this is the structure of the compound given to us. Also from the question, we also have that the absorbance is equal to 0.52 at the given wavelength, and that is 236 nanometer. At the same time, the path length, which is L, is given is what is 1 centimeter. Now another important thing that we also have to take note is the molar absorptivity, which is our epsilon, and that's 12,600. That's 12,600. Now, but we are now looking for the concentration. So in this case now, they gave us the absorbance, we have the path length, we have the molar absorption. The only thing we are looking for is the concentration, which is C. So that implies that I can simply use my A equals to epsilon C L. So I'll just insert the given values, and that means I'm going to have 0.52 equals to, that will be 12,600 multiplied by C multiplied by 1. So take note, when you are using this formula, your path length should be in centimeter. Your path length should be in centimeter. At the same time, don't forget what I've said, that depending on the unit of concentration determines what you call your epsilon. If the unit of the concentration is mole per dm cube or molarity, that means that your epsilon is molar absorptivity. But if the unit of concentration is gram per dm cube, that means that your epsilon is ordinary absorptivity. But in this case, what we are given as epsilon is molar absorptivity. That means that the concentration I'm going to get will be in mole per dm cube. That means from here now that we can say C will be equals to 0.52 over 12,600, and that will be equals to 0.000413. That will be what in molarity. So that will be the concentration in mole per dm cube, or let's say what in molarity. Before I also move further, one might want to ask about the unit of the molar absorptivity. Like I said, the unit of the molar absorptivity is either per molar, per centimeter. That is the unit. But sometimes some people also use this meter square per mole. Some people also use that. But in this case, like I said, that the most common one that we normally use is the molar absorptivity, and is per molar per centimeter. That's the unit of molar absorptivity. So in this case, this is the concentration that we have gotten in what? A mole per dm. But the reason why our concentration is a mole per dm cube is because our epsilon is given as molar absorptivity. So, but don't forget, our concentration is not to be gotten in what? In mole per dm cube. We have to get our concentration in what? In gram per dm cube. And we know that concentration in gram per dm cube equals to concentration in mole per dm in molarity multiplied by, that is molar mass, multiplied by molar mass. So we have to find the molar mass of the given compound, which is our 4-methyl 3-pentene 2-ol. So what will be the molar mass from there? Our molar mass will be equals to CH3 is 15, because hydrogen is 1 and we have carbon to be 12. So we are going to have 15. CO, C and O will give us, that will give us 28 plus 28. Carbon is 12, hydrogen is 1, that will give us 13. Carbon here is 12 and this is 15. So 12 plus 15 will give us 27. And then plus another 15, we have this. So from there, so what will be the molar mass? The molar mass would be 58 gram per mole. So now that we know the molar mass, and we already gotten the concentration in mole per dm cube. That means that our concentration in gram per dm cube, which is what we have to find, gram per dm cube, will be equals to 0.000413 multiplied by 98, and that will give us 0.00405, and in gram per dm cube. So this is the concentration that we have to find. But don't forget, like I said, the unit is gram per dm cube, and that's one way to apply the expression that we got from Beer-Lambert law. Probably subsequent video that I'm going to do, we are going to also look at other examples or other questions that can also come from this particular aspect of spectroscopic technique. I hope that from this lesson you are going to get one or two things, and I hope for your questions, or probably if there is anything that is not clear, you can do well to drop your comments. I will try as much as possible to respond. So thank you again for watching. So I hope that you continue to share with friends that can also be in need of this lesson. And also, let's do well to please subscribe. Thank you for watching.